In the spring of 2019, inside a basement laboratory at Heriot-Watt University in Edinburgh, 6 photons were about to end a 300-year argument about the nature of reality. The room was cold, deliberately so, kept at a constant 17 degrees Celsius to prevent thermal drift in the optical equipment. The lights were off. The only illumination came from indicator LEDs on power supplies and the faint green glow of oscilloscope screens. A doctoral student named Martin Ringbauer sat at a workstation, his face lit by the pale wash of a laptop display, watching numbers scroll past faster than any human eye could track. Across the lab, a lattice of mirrors, beam splitters, and single photon detectors covered an optical table the size of a dining room surface, all of it bolted to a concrete plinth sunk 3 feet into the building's foundation to isolate it from vibration. The experiment had been running for hours. The photons were being generated, entangled, measured, and destroyed at a rate of roughly 8,000 per second. And somewhere in that blur of quantum events, something impossible was happening. I want you to hold an image in your mind as we begin tonight. Picture 2 people standing in the same room, looking at the same object at the same moment, under the same lighting conditions, with the same working eyes. One of them sees a red ball, the other sees a blue cube, not because one of them is colorblind, not because one of them is lying, not because the object is somehow ambiguous or the lighting is strange. They see different things because, at the most fundamental level of physical law, the object genuinely is a red ball for one of them and genuinely is a blue cube for the other. Both are correct, neither is mistaken, and there is no deeper fact of the matter that could settle the disagreement. This sounds like philosophy. It sounds like the kind of late-night dorm room speculation that evaporates under the bright lights of actual science. But what happened in that Edinburgh basement in 2019 was not philosophy. It was measurement. It was data. It was a peer-reviewed result published in one of the most prestigious physics journals in the world. And what it demonstrated, with statistical significance so high that the probability of error was less than 1 in a million, is that 2 observers can experience genuinely incompatible realities for the same quantum event, and both of their experiences can be equally valid descriptions of what actually happened. The experiment was called the first laboratory realization of the extended Wigner's friend scenario, and if that phrase means nothing to you yet, don't worry. By the time we reach the end of this journey together, you will understand exactly what those words mean, why they matter, and why a growing number of physicists now believe that this single experiment may have quietly demolished one of the deepest assumptions human beings have ever made about the universe. The assumption that there is one reality, that facts are facts, that if something happens, it happens the same way for everyone. Consider tapping that like and subscribe button if slow explorations like this one help you think, or help you sleep, or help you feel a little less alone in a strange universe. These journeys take months to research and write, and alike costs you nothing but a moment. Now, let us begin. The story of what happened in Edinburgh cannot be understood without first understanding the thought experiment that inspired it, and the thought experiment cannot be understood without first understanding the man who invented it and the problem he was trying to solve. So let us travel backward, not to 2019, but to 1961, to a different laboratory in a different country, where a Hungarian-American physicist named Eugene Wigner sat in his office at Princeton University, staring at a piece of paper covered in equations, and realized that quantum mechanics had a problem that no one wanted to talk about. Eugene Wigner was not a rebel. He was not a provocateur. He was by 1961 one of the most respected theoretical physicists in the world, a future Nobel laureate, a man whose mathematical contributions to quantum theory were so foundational that entire branches of physics bear his name. He had fled Hungary ahead of the Nazi advance, had worked on the Manhattan Project, had helped build the first nuclear reactors. He was an insider's insider, a member of the scientific establishment in good standing, and it was precisely because of his credentials, his reputation, his unimpeachable seriousness, that what he wrote in 1961 landed with such uncomfortable force. The paper was titled Remarks on the Mind-Body Question, and it was published in a book called The Scientist Speculates. The title alone suggested that Wigner knew he was stepping onto dangerous ground. Speculation was not something serious physicists did. But Wigner had realized something that he could not unrealize, and he felt compelled to write it down. The problem Wigner identified was this: quantum mechanics, the most successful scientific theory in human history, the the theory that correctly predicts the behavior of atoms, molecules, light, semiconductors, superconductors, lasers, and every piece of electronic technology you have ever touched, describes the universe in a very strange way. According to quantum mechanics, physical systems do not have definite properties until those properties are measured. An electron does not have a definite position until you look for its position. A photon does not have a definite polarization until you measure its polarization. Before measurement, these properties exist only as probabilities, as mathematical superpositions of all the possible values the property could have. This is not a statement about our ignorance. This is not a claim that the electron really does have a definite position, and we simply don't know what it is. According to the standard mathematical formalism of quantum mechanics, the superposition is real. The electron genuinely is in multiple places at once, in a very precise mathematical sense, until the act of measurement collapses the superposition into a single definite outcome. Now here is where Wigner's question emerges. What counts as a measurement? The mathematics of quantum mechanics describes two fundamentally different kinds of processes. There is smooth, continuous, deterministic evolution, governed by an equation called the Schrödinger equation, which describes how superpositions spread and evolve over time. And there is sudden, discontinuous, probabilistic collapse, which happens when a measurement occurs and the superposition snaps into a single definite value. The theory gives you rules for both processes, but it does not tell you when to apply which rule. Let me put that more starkly. Quantum mechanics, the most precisely tested theory in the history of science, does not actually tell you when quantum mechanics applies. Wigner imagined a thought experiment designed to expose this problem with merciless clarity. Suppose, he said, that I have a friend. My friend is a physicist trained in quantum mechanics, working in a laboratory. Inside the laboratory is a quantum system, let us say a single particle, in a superposition of two states. My friend performs a measurement on the particle. According to quantum mechanics, the superposition collapses, and my friend sees a definite outcome. The particle is either in state A or state B. My friend knows which one. The measurement is complete. But now consider my perspective. I am outside the laboratory. The door is closed. I have not looked inside. From my point of view, I have no information about what my friend observed. And here is Wigner's question. From my perspective, has the collapse happened yet? According to one interpretation of quantum mechanics, the collapse happens when the measurement happens, regardless of whether anyone outside the lab knows about it. My friend measured the particle, the superposition collapsed, and there is now a fact of the matter about which outcome occurred, even though I don't know what it is. But according to the mathematical formalism of quantum mechanics, applied consistently, this is not what happens. From my perspective outside the laboratory, my friend is also a physical system. My friend is made of atoms. Those atoms obey quantum mechanics. If I describe the situation mathematically, without peeking inside the lab, what I see is that my friend and the particle have become entangled. My friend has not observed a definite outcome. My friend is in a superposition of having observed outcome A and having observed outcome B. The collapse has not happened yet, from my perspective, because I have not made a measurement yet. This is the Wigner's friend problem, and the reason it troubled Wigner, and the reason it troubled so many physicists after him, is that it seems to lead to a contradiction. If my friend opens the laboratory door and tells me what she observed, we can compare notes. She will tell me that she saw outcome A, let us say, and that she saw it at a specific time, the moment she made her measurement. But from my perspective, the outcome was not determined until I opened the door. So when did the collapse happen? When my friend looked, or when I looked at my friend? If the collapse happened when my friend looked, then what is so special about my friend? Why does my friend's observation count as a measurement that triggers collapse, while the interaction between the particle and the measuring apparatus did not? My friend's eye is just a bunch of atoms. The measuring apparatus is just a bunch of atoms. Where is the magic line that separates measurement from mere physical interaction? And if the collapse only happened when I looked, then my friend was in a superposition until that moment. My friend was, in some sense, both having seen A and both having seen B simultaneously, until I opened the door. But my friend certainly doesn't feel like she was in a superposition. She remembers making a measurement. She remembers seeing a definite result. She remembers the exact moment it happened. Was her memory formed after the fact somehow when I looked? Was she not really conscious until I observed her? Wigner himself, in that 1961 paper, proposed a radical solution. He suggested that consciousness, human consciousness specifically, plays a special role in quantum mechanics. He suggested that it is the act of a conscious mind observing a system that triggers collapse, and that the laws of physics cannot be understood without reference to the existence of minds. This proposal was controversial then, and remains controversial now. Most physicists reject it. But notice what is happening here. The most mathematically rigorous physicist of his generation, a man who spent his life insisting that physics be placed on a firm formal foundation, was driven by the logic of his own theory to suggest that consciousness might be built into the laws of nature. That is how strange the Wigner's friend problem is. That is how deep it cuts. For decades, the thought experiment remained just that, a thought experiment, a philosophical puzzle, a late-night conversation topic for physicists who had finished their third beer and wanted to argue about interpretations. There seemed to be no way to actually test it, because the scenario Wigner described was impossible to realize in practice. You cannot put a human being in a quantum superposition. You cannot isolate a physicist from the rest of the universe thoroughly enough to prevent environmental decoherence from destroying the quantum effects before you can measure them. The friend in Wigner's thought experiment is, in principle, a quantum system, but in practice, a human being is far too large, too warm, too interactive with the surrounding world to maintain quantum coherence for more than a trillionth of a second. And so, the problem sat. It sat through the 1960s. It sat through the 1970s. It sat through the rise and fall of various interpretations of quantum mechanics, the many worlds interpretation, the pilot wave interpretation, the consistent histories interpretation, each of which offered a different answer to Wigner's question, and none of which could be experimentally distinguished from the others. It sat through the development of quantum computing, quantum cryptography, quantum teleportation. It sat through all of it, a philosophical thorn in the side of physics, impossible to remove but seemingly impossible to address. And then, in 2018, a theoretical physicist named Czeslaw Bruckner published a paper. Bruckner was a professor at the University of Vienna, one of the world's leading centres for quantum foundations research. He had been thinking about Wigner's friend for years, turning the problem over in his mind, looking for a way to sharpen it, to make it cut deeper. And what he realised was that Wigner's original scenario, as troubling as it was, did not go far enough. Wigner had imagined one friend inside one laboratory. Bruckner imagined two. Let me describe the extended scenario. Imagine two laboratories, separated by some distance. Inside each laboratory is a physicist, a friend. Call them Alice and Bob, the traditional names for parties in thought experiments. Each friend has access to a quantum system. The two quantum systems are entangled with each other, linked in that peculiar quantum way that Einstein called spooky action at a distance. Each friend performs a measurement on their local system and records the result. Now imagine two more observers outside the laboratories. Call them Alice Prime and Bob Prime. These are the Wigner figures, the outsiders who have not looked inside the labs yet. At some point, Alice Prime and Bob Prime each make their own measurements that can be performed on the entire laboratory, treating the friend inside as just another quantum system. Bruckner showed that if you set up this scenario carefully, if you choose the right initial entangled state and the right measurements for everyone to perform, you can derive a mathematical relationship, a prediction. Specifically, you can derive an inequality, similar to the famous Bell inequalities that were tested in the 1970s and 80s, but with a crucial difference. The Bell inequalities test whether quantum mechanics can be explained by local hidden variables, underlying properties that exist before measurement, and determine the outcomes. The new inequality, which came to be called a Bruckner inequality, or an extended Wigner's friend inequality, tests something else. It tests whether the outcomes observed by different observers can be combined into a single consistent description of what happened. Let that sink in for a moment. The Bell inequalities ask whether there are hidden facts that determine measurement outcomes before anyone looks. The violation of Bell inequalities, experimentally confirmed dozens of times, tells us that there are no such hidden facts. Quantum randomness is fundamental. But the extended Wigner's friend inequality asks a different question. It asks whether, even in the absence of hidden variables, the facts that do get established by measurements can all be true simultaneously. It asks whether there is a single story that accommodates all the observations, even if that story is irreducibly random. It asks whether reality, however strange, is at least the same reality for everyone. And Bruckner's mathematics predicted that the inequality could be violated, that an experiment, if carefully constructed, could produce data that is statistically inconsistent with the assumption that all observers share a common reality. The paper landed in 2018, and a group of experimental physicists in Edinburgh read it, and said to each other something like this: "We can build this." The lead experimentalist was Massimiliano Prietti, a young researcher who had been working on photonic quantum information experiments at Heriot-Watt. The senior author was Alessandro Fedrizzi, who had come to Edinburgh after years of work in Vienna in the same quantum foundations community that had produced Bruckner's theoretical work. They knew the theory, they knew the predictions, and they had access to one of the most sophisticated single-photon experimental setups in Europe. The challenge was daunting. You cannot put human beings in superpositions, that remains true, but Bruckner's theoretical work had shown that you do not need human beings. What you need is a system that can record the outcome of a measurement, a system that can be said, in a meaningful sense, to have observed a result. The friends in the thought experiment do not need to be conscious. They do not need to be alive. They need to be observers in the minimal physical sense, systems that correlate with the measured system in a particular way. A photon, measured by a device that records its polarization, is such a system. The measuring device becomes correlated with the photon's polarization. The device has, in the relevant sense, observed the photon, so Prietti and Fedrizzi designed an experiment that used photons as the quantum systems being measured, and other photons as the measuring devices, photons observing photons. The friends in this realization were not human, they were single particles of light. Let me pause here and make sure you understand what this means. The experiment was not a test of what human observers experience. It was a test of whether the mathematical structure of quantum mechanics, applied consistently, produces data that cannot be accommodated within any framework where facts are observer independent. The question is not whether you and I might perceive different realities for psychological reasons. The question is whether the universe itself, at the deepest level we can probe, permits a single consistent story to be told. If that sounds abstract, stay with me. The experimental details, when we reach them, will make it concrete. The laboratory at Heriot-Watt was in a building called the David Brewster Building, named after the Scottish physicist who invented the kaleidoscope. There is something fitting about that. A kaleidoscope creates multiple images from a single object by reflecting light through mirrors. The experiment in the basement of that building would do something conceptually similar, creating multiple realities from a single quantum event. The optical table, 3 meters by 1.5 meters, was covered with precisely aligned components. At the heart of the setup was a crystal, a piece of beta barium borate, a nonlinear optical material that can split a single ultraviolet photon into a pair of lower energy photons travelling in different directions. These photon pairs emerge entangled. Their polarizations are correlated in a way that cannot be explained by any story in which each photon had a definite polarization before being measured. This is the same type of entanglement used to violate Bell inequalities, a workhorse of quantum information science, reliable and well understood. But generating entangled pairs was only the first step. The experiment required something more elaborate. It required constructing, in photons, the full structure of Bruckner's extended scenario. 2 laboratories, 2 friends, 2 outside observers, all realized in beams of light bouncing between mirrors. The way this was achieved is subtle but beautiful. Each of the 2 entangled photons was sent into a subsystem that represented a laboratory. Inside each subsystem, the photon's polarization was measured by another photon, the friend. This measurement was implemented using a device called a controlled NOT gate, a quantum logic gate that causes 2 photons to interact in a specific way. After passing through the gate, the friend photon carries information about the system photon's polarization. The friend has, in the relevant sense, observed the system. But here is the key. The entire subsystem, the system photon, the friend photon, and all the optical components can be treated from the outside as a single quantum system. The outside observers, Alice Prime and Bob Prime, can make measurements on the entire subsystem without disturbing the correlation established by the inner measurement. They can measure the laboratory as a whole, in a basis that treats it as a superposition of the friend having observed outcome A and the friend having observed outcome B. This is what Wigner imagined. This is what Bruckner mathematicized. And this is what Prietti and Fedrizzi built. The experiment ran for months, thousands of trials, millions of photon pairs. Each trial required generating the initial entangled state, sending the photons through the appropriate subsystems, implementing the friend measurements, implementing the outside observed measurements, and recording the results with single photon detectors so sensitive that they could register a single quantum of light arriving in a window of time less than a billionth of a second wide. The data accumulated, and the inequality was violated. Not violated in a marginal, ambiguous, maybe it's statistical noise way. Violated by more than 5 standard deviations. Violated with a confidence level that, in the language of physics, counts as a discovery. The probability that the observed results could arise by chance, if the inequality were actually satisfied, was less than 1 in 3.5 million. What did the violation mean? Let me try to say it as clearly as I can. The inequality being tested was derived under a specific set of assumptions. If those assumptions are all true, the inequality cannot be violated. But it was violated, so at least one of the assumptions must be false. There are, broadly speaking, 3 assumptions that go into the derivation. The first assumption is called locality. It says that the measurements made in one laboratory cannot instantly influence the measurements made in the other laboratory. If locality fails, then the correlations between Alice's results and Bob's results could be explained by some kind of faster-than-light influence, some spooky communication between the subsystems. The second assumption is called freedom of choice. It says that the experimenters can freely choose which measurements to perform, and that these choices are not correlated with the initial quantum state in some conspiratorial way. If freedom of choice fails, then the universe might be set up in a way that only makes it look like the inequality is violated, because the measurement choices were somehow predetermined to produce misleading data. The third assumption is called observer-independent facts. It says that when a measurement is performed, a definite outcome occurs, and that outcome is a fact for everyone, not just for the observer who made the measurement. If observer-independent facts holds, then the friend inside the laboratory sees some definite result, A or B, and that same result is the true result, even for the outside observer who has not yet looked. Locality and freedom of choice have been tested before in other experiments, and while they cannot be proven with absolute certainty, the evidence for them is strong. The experiments that violate Bell inequalities are designed to close loopholes related to locality. The freedom of choice assumption is hard to test directly, but violating it would require either backward-in-time causation or a super-deterministic conspiracy in the initial conditions of the universe. The extended winner's friend experiment added a new ingredient. For the first time, it was possible to test the assumption of observer-independent facts separately from the other two. And what the data suggested, what the violation of the inequality implied, was that this third assumption might be the one that fails. Say that slowly to yourself. Observer-independent facts might not exist. When your friend measures a photon and sees that it is horizontally polarized, that might not be a fact about the photon. That might be a fact about your friend. From your perspective outside the lab, the photon and your friend together are in a superposition. There is no fact yet about what the photon's polarization is. Your friend's experience of seeing a definite outcome is real to her, but it is not real in any universal sense that you must agree with. And when you finally make your own measurement, you establish your own facts. But your facts are not her facts. Her facts are not your facts. And there is no God's eye view, no view from nowhere, no fundamental reality that both of you are describing differently. This is what the experiment suggested. This is what made headlines in physics journals around the world in the summer of 2019. This is what caused heated arguments at conferences for years afterward. Let me be careful here. The experiment does not prove that observer-independent facts do not exist. It proves that if you accept locality and freedom of choice, then observer-independent facts must be false. But you could, in principle, reject one of the other assumptions instead. You could accept that the universe is non-local, that what happens here can instantly influence what happens in a galaxy 2 billion light-years away. You could accept that freedom of choice is an illusion, that every experiment is choreographed by the initial conditions of the Big Bang. These options are available. But most physicists, when confronted with these choices, feel deeply uncomfortable. Non-locality of the kind required would seem to undermine the entire structure of relativity, the other great pillar of modern physics, and superdeterminism, the denial of freedom of choice, feels like cheating. It is a hypothesis that cannot be tested, because any test you design is by assumption already contaminated by the conspiracy. So the discomfort lands for many on the third assumption. And the conversation that began in that Edinburgh basement has not stopped. It has only grown. The laboratory where this happened is still there. The optical table has been reconfigured for other experiments, other questions, other tests of quantum strangeness. But the data from 2019 still exists, still sits in files on servers, still makes the same uncomfortable argument. And now, having set the stage, having introduced the players, having explained what was being tested and what the result was, we need to go deeper. We need to understand why this matters beyond the laboratory. We need to understand what reality itself might be if the experiment is pointing toward the truth. And we need to understand why so many physicists, some of the smartest people on Earth, have spent the years since 2019 arguing furiously about whether this result can be explained away, or whether it demands a fundamental revision of how we understand the universe. The argument is still happening. The conferences are still convening, and the photons, of course, have no opinion. They simply are what they are. Or perhaps what they are depends on who is asking. Settle in. Let that last thought sit with you for a moment before we continue, because we are only beginning to see how deep this goes. The question we must now confront is deceptively simple. What is a fact? You use the word every day without thinking about it. The sky is blue. Water boils at 100 degrees Celsius at sea level. The Earth orbits the Sun. These are facts. They feel solid. They feel like descriptions of how things actually are, independent of whether anyone happens to be looking at them or thinking about them. The sky does not stop being blue because you close your eyes. The water does not wait for your attention before it boils. These things happen whether you observe them or not. This is the intuition that has carried science forward for 400 years. The universe exists. It has properties. Our job is to discover those properties through careful measurement and rigorous reasoning. We might make mistakes along the way. Our instruments might be imprecise. Our theories might be incomplete. But underneath all of that, there is a single consistent reality that we are all trying to describe, and in principle, with enough effort and enough care, we can converge on the truth. This assumption is so deep that most scientists never think to question it. It is the water they swim in. It is the air they breathe. It is not a hypothesis to be tested. It is the foundation on which all hypotheses are built, and yet. Think about what happened on that optical table in Edinburgh. Two observers, Alice and Bob, built into a physical system through carefully controlled photon states and interferometers. Each observer makes a measurement. Each observer records a definite result. And when Proietti's team analysed the data, when they looked at the correlations between all the measurements across thousands and thousands of experimental runs, they found something that should not have been possible. The numbers violated an inequality. And that inequality was designed precisely and mathematically to test whether both observers could be describing the same underlying reality. They could not. Or rather, if you insist that they must be describing the same reality, you must give up something else, something equally fundamental. And this is where the discomfort begins to sharpen into something like vertigo. Let me try to make this concrete. Imagine you have a coin, a perfectly ordinary coin, copper and nickel worn smooth by years in someone's pocket. You flip it. It lands on the table and you cover it with your hand before looking. What is the state of the coin right now, in this moment, before you lift your hand? Common sense says the coin is definitely heads or definitely tails. The outcome was determined the moment it landed. Your ignorance of the result does not change the result. The coin has a state. You simply do not know what it is yet. This is how classical physics works. This is how the world seems to work when you're dealing with objects large enough to see and touch. Now consider a quantum coin, a photon that will pass through a polarizing filter and either be absorbed or transmitted. Before you make the measurement, before you look, what is the state of the photon? And here is where the strangeness begins. According to quantum mechanics, the photon does not have a definite state. It is not that you are ignorant of the answer. It is that there is no answer yet. The photon exists in a superposition, a mathematical combination of both possibilities at once, and only when you make a measurement does one possibility become real. This is not a metaphor. This is what the equations say. This is what every experiment has confirmed for nearly a century. The photon is not hiding its polarization from you. It genuinely does not have one until you ask. But here is the question that Wigner asked in 1961, the question that Prietti's team finally put to experimental test. What happens when someone else asks first? Your friend measures the photon. From her perspective, the superposition has collapsed. She has seen a definite result. The photon is now horizontally polarized, or vertically polarized, and that is a fact about the world. She could write it down, she could tell you about it, she could remember it for the rest of her life. But from your perspective, standing outside the laboratory, applying the same quantum mechanics that correctly predicts every other experiment, your friend and the photon together are in a superposition. The measurement has not yet yielded a definite result, because you have not yet interacted with the system. You have not yet made your observation. And here is the crucial point, the point that makes physicists uncomfortable, the point that caused arguments in Edinburgh and Vienna and Waterloo and every other place where this result was discussed. According to quantum mechanics, both descriptions are correct. Your friend is right that the photon has a definite polarization, and you are right that the system is still in superposition. Both of you are correctly applying the laws of physics. Both of you are making accurate predictions about your future observations. But how can that be? How can the photon be both definite and indefinite at the same time? How can two descriptions, logically incompatible with each other, both be true? The answer that the experiment suggests, the answer that made so many physicists uncomfortable, is that there is no single truth. There are only truths relative to observers, and what is real for your friend is not necessarily real for you. Stop and feel the weight of that. For 400 years, science has operated on the assumption that it was discovering objective facts about an observer-independent reality. The whole point of the scientific method, the whole power of empirical investigation, was supposed to be that it gave us access to how things actually are, stripped of human bias and subjective impression. Science was not about opinions. Science was about truth. Capital T truth. The kind that does not depend on who is looking. And now an experiment, a real experiment with real photons and real detectors and real data, is suggesting that this assumption might be wrong. Not wrong in some distant corner of the universe where gravity is crushing space-time into knots. Not wrong at energies that require particle accelerators the size of continents. Wrong right here, on a tabletop in Scotland, with equipment that costs less than a sports car. The philosophers noticed first, of course. They had been arguing about these questions for decades, for centuries really, long before quantum mechanics gave the discussion a mathematical backbone. There is a tradition in philosophy called perspectivism, associated most famously with Nietzsche, which holds that all knowledge is knowledge from a particular perspective, that there is no view from nowhere, no God's eye that sees things as they truly are. And there is a tradition called relativism, often misunderstood and often criticized, which holds that truth itself might be relative to observers or cultures or frameworks. Most scientists dismissed these philosophical positions as confusion, as failures to understand what objectivity really meant, as the kind of hand-wringing that happened in humanities departments, while real researchers got on with the business of discovering facts. But here was a physics experiment, using the most rigorous methods available, producing data that seemed to vindicate the philosophers, or at least producing data that demanded a response. The response came quickly, and it came from many directions. Some physicists argued that the experiment had been misinterpreted. They pointed to subtle assumptions in the analysis, possible loopholes in the setup, ways that observer-independent facts might still be salvaged if you looked carefully enough at what had actually been measured. These objections were technical and detailed, involving questions about what counts as an observer, what counts as a measurement, and whether the photon states in Prietti's experiment really captured the essential features of Wigner's original thought experiment. Other physicists accepted the result but drew different conclusions. They argued that the experiment did not show that facts are relative to observers. Instead, It showed that our concepts of fact and observation need to be refined, that we need a more sophisticated understanding of what it means to make a measurement and record a result. Perhaps the problem was not with observer-independent reality, but with our naive assumptions about what observers are and how they interact with quantum systems. And a third group, smaller but growing, accepted the most radical interpretation. They argued that the experiment was showing us something genuine about the structure of reality, something that previous generations of physicists had been able to ignore only because they had never done the relevant test. Reality, according to this view, is not a single objective thing that exists independent of observers. Reality is a web of perspectives, a network of observations, each one internally consistent but not necessarily compatible with the others. This third group often invoked a particular interpretation of quantum mechanics called cubism, short for quantum Bayesianism. The founders of this interpretation, Christopher Fuchs and Rüdiger Schack and a handful of others, had been arguing since the early 2000s that quantum mechanics should be understood not as a description of an objective reality, but as a user's manual for making predictions about one's own future experiences. On this view, the wave function is not a physical thing out there in the world. It is a mathematical tool that an agent uses to organize their expectations, and when the wave function collapses upon measurement, nothing physical is happening. The agent is simply updating their expectations in light of new information. Cubism had always been a minority position in physics. Most physicists, trained to think of their theories as descriptions of how things really are, found it strange and unsatisfying. But after Proietti's experiment, after the data came in and the papers were published and the arguments began, more and more physicists started taking cubism seriously. Not because they were convinced it was right, but because the alternative, giving up on observer-independent reality entirely, seemed even stranger. Let me try to give you a feel for how disorienting this situation is. Imagine you're a physicist. You've spent your entire career studying the laws of nature, trying to understand how the universe works, trying to uncover the deep mathematical structures that govern everything from the smallest particles to the largest galaxies. You believe, as most physicists do, that you are engaged in a noble project of discovery. You're not making things up. You're not constructing a social narrative. You're finding out what is true, and then someone shows you an experiment. A careful, well-designed, multiply-replicated experiment. And the experiment tells you that truth itself might be observer-dependent, that the facts you thought you were discovering might not exist until you discover them, that another physicist, equally careful and equally rigorous, might discover different facts, not because one of you made a mistake, but because there is no single set of facts to discover. What do you do with that? How do you continue your work? How do you write your papers and give your talks and teach your students, knowing that the entire edifice might rest on a foundation that is not there? This is the crisis that Proietti's experiment precipitated. Not a crisis in the data. The data is clean, the statistics are solid. The violation of the bell-like inequality is clear and unambiguous. The crisis is conceptual. The crisis is about what physics is supposed to be doing in the first place. Some physicists responded by doubling down on interpretations that preserve objectivity. The many worlds interpretation, for instance, says that every quantum measurement causes the universe to split into branches, with each possible outcome realized in a different branch. On this view, there is an objective reality. It is just much, much larger than we thought. Every observer exists in all branches, seeing all possible outcomes, and the appearance of a single definite result is just the observer's limited perspective on an exponentially vast multiverse. Many worlds has its own problems, of course. It requires you to believe that the universe is constantly splitting into countless copies of itself, that there are versions of you making every possible choice and experiencing every possible outcome, that the total reality is incomprehensibly larger than anything we can directly observe. For some physicists, this seems like a high price to pay for preserving objectivity. For others, it is exactly the kind of radical revision that quantum mechanics demands. Other physicists turn to pilot wave theory, also called Bohmian mechanics after its modern developer David Bohm. This interpretation says that particles do have definite positions and trajectories at all times, guided by a non-local wave function that tells them where to go. On this view, the randomness of quantum mechanics is not fundamental. It is just a reflection of our ignorance about the precise initial conditions. There are hidden variables beneath the apparent randomness, and if we knew them, we could predict every outcome exactly. pilot wave theory preserves objectivity, but at the cost of non-locality. The guiding wave responds instantly to what happens anywhere in the universe, no matter how far away. A measurement here, on Earth, can instantaneously affect the trajectory of a particle in a galaxy billions of light-years distant. This does not allow faster-than-light signalling, so it does not violate relativity in the most obvious way. But it does seem to violate the spirit of relativity, the idea that there is no absolute simultaneity, no universal now that stretches across the cosmos. And then there is superdeterminism, the most radical option of all. Superdeterminism says that the settings of detectors and the properties of particles are secretly correlated from the beginning of time, conspiring to produce experimental outcomes that look random but are actually predetermined. On this view, the experimenter does not have genuine freedom to choose how to make measurements. Every choice was already written into the initial conditions of the Big Bang, encoded in the precise arrangement of matter and energy at the first moment. Superdeterminism is deeply unpopular among physicists for good reason. It seems to undermine the entire enterprise of experimental science. If your measurements are always corrupted by cosmic conspiracies, how can you ever trust your data? How can you ever design a test that counts as evidence for or against anything? Superdeterminism may be logically consistent, but it feels like giving up. So here we are. 4 options. 4 ways to respond to the data that came out of Edinburgh in the summer of 2019. You can accept non-locality with all its tensions with relativity. You can accept superdeterminism with all its implications for free will and scientific method. You can accept observer-dependent reality with all its challenges to the traditional picture of scientific knowledge. Or you can accept many worlds with all its extravagance about the size and structure of existence. None of these options is comfortable. None of them fits easily into the intuitions that scientists have developed over centuries of successful work. And that, more than anything else, is what made Prietti's experiment so significant. It did not tell us which option to choose. It told us that we have to choose. The conversations that followed were fascinating to watch, if you knew where to look. The papers were published in serious journals, physical review letters, and Nature Physics and the like. The preprint server arxiv.org filled with responses and critiques and alternative analyses. And at conferences, in hallways and coffee breaks and late-night sessions at hotel bars, physicists argued with the kind of intensity that only happens when something fundamental is at stake. Some defended the experiment fiercely. This was real data, they said. This was a genuine test of observer-independent reality. You cannot wave it away with philosophical hand-wringing. You have to confront what the numbers are telling you. Others attacked just as fiercely. The experiment was limited, they said. The photon states were not truly observers. The Bell-like inequality was not precisely the right test. Give us better equipment, give us more sophisticated protocols, and we will find the loophole. We will restore observer-independent facts to their proper place. And others simply shrugged. Quantum mechanics has always been strange, they said. This is just one more strange result in a century full of strange results. We will absorb it into our understanding and move on. The photons do what they do. Our job is to predict their behaviour, not to tell stories about what they really are. But there was something different about this experiment, something that prevented easy dismissal. Previous tests of quantum weirdness, like the Bell tests from the 1980s and 1990s, had challenged hidden variables and local realism. They had told us that the world is non-local in some sense, that entangled particles are connected in ways that defy classical intuition. But they had not challenged the idea that there is a fact of the matter about what happened. They had not suggested that 2 observers could legitimately disagree about whether a measurement occurred and what result it produced. The Prietti experiment went further. It took the next step. It said not just that reality is strange, but that reality might be plural, that there might be no single story that contains all the facts, that the universe might be genuinely perspectival, genuinely relative, in a way that even Einstein's relativity never suggested. And that is a different kind of strangeness. That is the kind of strangeness that touches the foundations. Consider what it would mean if the experiment is pointing toward the truth. Consider a universe where observer-independent facts do not exist. In such a universe, there is no answer to the question of what really happened. There are only answers relative to particular observers, particular perspectives, particular vantage points on the quantum foam. Your experience is real to you, my experience is real to me, and there is no higher court that can adjudicate between them. This is not solipsism exactly. It is not the claim that only your mind exists. Other observers are real, their experiences are real, but their reality is their reality, and your reality is your reality, and the two need not mesh into a single coherent whole. It is a strange picture. It is an uncomfortable picture. It is in some ways the opposite of everything that science has tried to achieve for 4 centuries, and yet the data sits there, on servers in Edinburgh and Innsbruck and Waterloo and dozens of other places where the experiment has been replicated and refined. The numbers are clear, the statistics are solid, the violation of the inequality is beyond reasonable doubt. Something has to give. In the years since 2019, the conversation has continued. New experiments have been proposed, testing different aspects of the puzzle, looking for different loopholes, trying to pin down exactly where objectivity fails, if it fails at all. Theoretical physicists have written papers attempting to reformulate quantum mechanics in ways that dissolve the paradox, that show how observer-dependent appearances can emerge from an observer-independent reality beneath. None of these attempts has succeeded convincingly. The puzzle remains, the discomfort remains, and the photons, as always, have no opinion. They simply do what they do, following laws that we can predict with exquisite precision, but cannot explain with any interpretation that everyone finds satisfying. Now let us step back from the physics for a moment and think about what this means for us. Not as physicists, not as philosophers, but as human beings trying to understand the world we live in and our place within it. We rely on facts. We build our lives around them. We make decisions based on what we believe to be true, and we expect that truth to be stable, to be the same from one moment to the next, to be the same for everyone who cares to check. When I tell you that the sun rose this morning, I expect you to agree. When you tell me that water is wet, I expect that we are talking about the same thing. Facts are the currency of shared reality. They are what allow us to communicate, to cooperate, to build civilizations and write histories and plan futures. And here is an experiment telling us that facts, at the deepest level we can probe, might not work the way we thought, that the bedrock might not be bedrock at all, that the foundation might be a web of perspectives, each one internally consistent, none of them more true than the others. Let that settle for a moment before we continue, because we are not done with the implications. We have only begun to trace how far they reach. The question that hangs in the air now is not whether the experiment worked. It did. The question is not whether the statistics are solid. They are. The question that has kept physicists awake, that has filled conference halls with arguments that sometimes verge on shouting, is simpler and harder. What do we do with this? Because science has always operated under a particular assumption, one so deep that most scientists never even notice they are making it. The assumption is that when we do an experiment, we are discovering something. We are uncovering a fact that was already there, waiting to be found, like an archaeologist brushing dirt off a fossil. The fossil existed before we found it. The dinosaur lived and died millions of years before any human hand touched its bones. That is what discovery means. That is what objectivity means. The world is a certain way, and our job is to figure out what that way is. But the Wigner's friend experiment, as Proietti and his collaborators performed it, suggests something else. It suggests that at the quantum level, there may be nothing waiting to be discovered. There may be no fossil under the dirt. There may only be the act of digging, and what you find depends on how you dig, and different diggers might find different things, and all of those things might be equally real. This is not a failure of measurement. This is not experimental error. This is not a case where we simply need better instruments or cleverer techniques. The mathematics says that this is how reality works. The mathematics says that incompatible outcomes can both be true, relative to different observers, and the experiment confirms what the mathematics says. Now, you might be thinking, surely there is a way out. Surely some brilliant physicist somewhere has found a loophole, a reinterpretation, a way to make this all make sense without abandoning the idea of objective reality. And you would be right that people have tried. Oh, have they tried? The years since 2019 have seen an explosion of theoretical work attempting to come to terms with what the experiment implies. Let me walk you through some of these attempts because they tell you something important about where physics stands today At the edge of a conceptual precipice it did not ask to stand on. The first and most obvious response is to question the experiment itself. Perhaps there is some hidden assumption in the setup, some subtle error in the reasoning, some classical loophole that allows the violation of the Bell-Wigner inequality without implying anything strange about reality. This is always the first move when an experiment produces uncomfortable results, and it is a perfectly legitimate move. Science advances by skepticism. Extraordinary claims require extraordinary evidence. So let us ask, is the Prietti experiment sound? The answer, after years of scrutiny, is yes. The experimental design has been examined by dozens of independent researchers. The statistical analysis has been checked and rechecked. The loopholes that plagued earlier Bell test experiments, the detection loophole and the locality loophole and various others, have been addressed. The experiment is clean. The result is real. You can argue about what it means, but you cannot argue that it did not happen. The second response is to bite the bullet and accept that quantum mechanics is telling us something true and strange about the world. This is the response that takes the experiment at face value and asks what kind of universe would produce such results. And there are several answers, several interpretations of quantum mechanics that can accommodate the Wigner's friend scenario without contradiction. One of them is the many worlds interpretation, proposed by Hugh Everett in 1957 and controversial ever since. In the many worlds picture, there is no collapse of the wave function, ever. When a quantum measurement is made, the universe does not randomly pick one outcome. Instead, the universe splits. Every possible outcome happens, but in different branches of reality, different worlds that exist in parallel but never interact. In this picture, when the friend inside the lab observes the photon, the universe branches. In one branch, the friend sees horizontal. In another branch, the friend sees vertical. Both branches are equally real. Both friends are equally real. And when Wigner later does his interfering measurement from outside, he is not contradicting his friend's observation. He is simply working with a superposition of branches, a quantum state that includes both versions of the friend having recorded both versions of the outcome. This interpretation saves objectivity in a peculiar way. It says that there is an objective reality, a universal wave function that describes everything, including all the branches and all the versions of every observer. But that objectivity is purchased at an enormous cost. The cost is that reality is unimaginably larger than we thought. Every quantum event spawns new worlds. The number of parallel branches is beyond calculation. And we have no way to know which branch we are in, no way to communicate with our other selves, no way to access the vast majority of reality that exists alongside us, but forever out of reach. Many physicists find this interpretation unsatisfying, not because it is illogical, but because it postulates an enormous amount of invisible machinery to explain the phenomena we observe. It feels to some like cheating, like explaining a magic trick by saying that an infinite number of invisible assistants are doing the real work behind the scenes. Another interpretation that can handle the Wigner's friend result is relational quantum mechanics, proposed by Carlo Rovelli in 1996. This interpretation takes the opposite approach from many worlds. Instead of saying that all outcomes happen, it says that outcomes are relational, that they exist only relative to particular observers. In relational quantum mechanics, there is no objective wave function describing the universe from a God's eye view. There is only the web of relationships between physical systems, the information that one system has about another. When the friend observes the photon, that observation is real relative to the friend. When Wigner measures the combined system from outside, his observation is real relative to him, and there is no higher standpoint from which to compare these observations and declare one of them more true than the other. This interpretation saves consistency by abandoning the expectation that consistency should mean agreement. It says that different observers having different facts is not a problem to be solved, but a feature to be accepted. The universe is perspectival all the way down. And the Wigner's friend experiment, far from being a paradox, is simply a demonstration of what the theory has been saying all along. Rovelli himself has written extensively about how his interpretation handles the Prietti result. He argues that the experiment is exactly what we should expect if relational quantum mechanics is true. The apparent contradiction between the friend's record and Wigner's measurement is not a contradiction at all, once you stop insisting that there should be a single story that both observers agree on. There is the friend story, which is true relative to the friend. There is Wigner's story, which is true relative to Wigner, and that is all there is. That is all there needs to be. But many physicists find this interpretation disturbing in a different way. It seems to undercut the very idea of science as a collective enterprise. If different observers can have different facts, and none of those facts is more true than the others, then what happens to the scientific method? What happens to peer review? What happens to the ideal of a shared, publicly accessible body of knowledge that anyone can check and verify? Rovelli would say that the relational interpretation does not undercut science, that it simply clarifies what science has always been doing. Science, he would argue, is not about discovering a God's eye view of reality. Science is about the relationships between physical systems, including the physical systems we call scientists. When two scientists agree on an experimental result, that agreement is a physical fact, a correlation between the states of their brains, and those correlations are real. They are just not the same thing as an observer-independent truth about the universe. This is a subtle point, and it requires careful thinking to grasp. Let me try to make it clearer. When you and I agree that a ball is red, something real is happening. Information is being shared between our brains. Our neural states are becoming correlated, and that correlation allows us to cooperate, to build on each other's observations, to do science together. But in the relational interpretation, this correlation does not require that there is a fact about the ball's colour that exists independently of any observer. The redness is real relative to you. The redness is real relative to me. Our agreement is a further fact, real relative to both of us, and the whole structure hangs together without needing a God's eye view to anchor it. Whether you find this satisfying or maddening depends, I think, on what you expect from a physical theory. If you expect physics to tell you what the world is really like, in a way that transcends any particular perspective, then relational quantum mechanics will frustrate you. It refuses to play that game. It says the game cannot be played, that the question itself is malformed, that asking for observer-independent facts is like asking for the weight of justice or the smell of Tuesday. But if you are willing to let go of that expectation, if you can accept that physics describes relationships rather than standalone substances, then the relational interpretation offers a coherent way to understand the Wigner's friend result. It says, this is what we should have expected all along. We just did not have an experiment to show us until 2019. There is a third response to the Prietti experiment, less popular among physicists but worth mentioning because it has a long philosophical pedigree. This is the response that says, the experiment shows that quantum mechanics is incomplete. There is something we do not know, some hidden variable or hidden mechanism that, if we could discover it, would restore objectivity and explain away the apparent contradictions. This was Einstein's hope, as I mentioned earlier. He never accepted that quantum mechanics was the final word on physical reality. He believed that there must be a deeper theory, a theory that would explain why quantum mechanics works so well while also preserving the classical intuitions about objectivity and determinism. Such a theory would have to be non-local, meaning that it would have to involve instantaneous influences across space, faster-than-light connections between distant particles, and it would have to evade Bell's theorem somehow, threading a narrow needle between the statistical predictions of quantum mechanics and the constraints that any hidden variable theory must satisfy. No one has succeeded in constructing such a theory. Every attempt has failed, either by making wrong predictions or by introducing assumptions as strange as the things it was trying to explain. The closest thing we have is Bohmian mechanics, a hidden variable interpretation that manages to reproduce quantum predictions by adding a layer of pilot waves guiding particles along definite trajectories. But Bohmian mechanics has its own problems, including a deep tension with special relativity and a feature that strikes many physicists as artificial. The hidden variables are there, they are doing work, but they are in principle undetectable. You can never observe them directly. They are like the invisible assistants in the many worlds interpretation, real but forever beyond verification. The Prietti experiment does not rule out hidden variable theories entirely, but it puts tremendous pressure on them. If you want to explain the experiment with hidden variables, you need those variables to behave in very peculiar ways. You need them to give different answers to different observers, or to conspire to produce correlations that look like observer-dependent facts, even though there is an objective reality underneath. The required conspiracy becomes more and more elaborate as the experiments become more and more refined. At some point, Occam's razor suggests that we should stop looking for the hidden reality and accept that what the experiments show is what is actually happening. This brings us to the fourth response, the one that might be the most honest and also the most unsatisfying. This is the response that says, we do not know. We do not know how to interpret the experiment. We do not know which interpretation of quantum mechanics is correct. We do not know whether objectivity is fundamental or emergent or illusory. We do not know whether there is a deeper theory waiting to be discovered or whether quantum mechanics is the final word. We are confused, and we have been confused for 100 years, and the Prietti experiment has made our confusion sharper, but has not resolved it. This is not a popular response among physicists, who are trained to look for answers and to have confidence in the answers they find. But it may be the most accurate response. The measurement problem, the puzzle of how definite outcomes emerge from quantum superpositions, remains unsolved. The interpretation problem, the puzzle of what quantum mechanics is really telling us about the world, remains contentious. And the Wigner's friend scenario, elevated from thought experiment to laboratory reality by Prietti and his collaborators, has thrown all of these puzzles into sharper relief without providing any new tools to solve them. What the experiment has done is narrow the space of acceptable answers. It has ruled out certain naive interpretations. It has shown that any interpretation that insists on observer-independent facts must be modified or abandoned. It has demonstrated that the quantum world, at least under certain carefully constructed conditions, does not behave the way our classical intuitions suggest it should. And it has done all of this with data, with statistics, with photons and beam splitters and phase plates and detectors humming in a laboratory in Edinburgh. The data is not philosophy. The data is not speculation. The data is physics, hard-won and painstakingly verified. And the data says that something we thought we knew, something we took for granted, something we relied on without ever examining, is either wrong or needs to be fundamentally reconceived. Now let us consider a different angle on all of this. Let us ask what the experiment tells us not about the nature of reality, but about the nature of knowledge. For centuries, philosophers have argued about epistemology, the study of what we can know and how we can know it. They have debated the roles of reason and observation, the reliability of the senses, the possibility of certainty, the foundations of belief. And through all of these debates, there has been an underlying assumption shared by nearly everyone, that there is something to know, that there are facts out there in the world, and our task is to discover them, to align our beliefs with reality, to achieve correspondence between our mental maps and the territory they represent. This assumption is so deep that it feels almost tautological. What could knowledge be, if not knowledge of something? What could truth be, if not agreement with the way things are? But the Wigner's friend experiment pokes at this assumption in a way that nothing else has. It suggests that at the quantum level, there may be no territory independent of the maps. There may be no facts prior to observation, no reality waiting to be known, no predetermined answers to the questions we ask. There may be only the asking, only the observing, only the web of relationships between observers and observed. If this is right, then epistemology needs to be rethought from the ground up. The goal of knowledge cannot be to mirror an observer-independent reality, because there is no such reality to mirror. The goal must be something else, something more modest or more complex or simply different. One possibility is that knowledge is about coherence rather than correspondence. Instead of asking whether our beliefs match the world, we should ask whether our beliefs fit together, whether they form a consistent and useful picture that allows us to navigate experience and communicate with others. On this view, knowledge is more like a shared story than a reflection of standalone facts, and different stories, different frameworks, different perspectives might all be legitimate as long as they are internally coherent and practically effective. This is not relativism in the dismissive sense, the view that all opinions are equally valid and there is no way to distinguish better from worse. Coherentist epistemology still has standards. Some belief systems are more coherent than others, some are more useful, some make better predictions, some facilitate cooperation, some lead to dead ends and contradictions, but the standards are internal to the web of beliefs, not derived from correspondence with an external reality. Another possibility is that knowledge is fundamentally relational, just as the relational interpretation says physical facts are relational. On this view, I know something relative to my perspective, my instruments, my history of interactions with the world. You know something relative to yours, and there is no standpoint outside all perspectives from which to compare our knowledge and declare one of us more right than the other. This does not mean that we cannot learn from each other. We can share information. We can correlate our observations. We can build shared frameworks that both of us find useful. But the sharing is itself a relationship, another link in the web, not an escape from the web into some neutral territory. These epistemological questions are not merely academic. They have practical implications for how we do science, how we think about expertise, how we navigate disagreements, how we build institutions and make collective decisions. If observer-independent facts are suspect, then the ideal of objective knowledge becomes more complicated. Not impossible, but different. Not a simple matter of discovering what is true, but a complex negotiation among perspectives, a process of building bridges between different views, a shared project of constructing reality rather than merely uncovering it. This might sound alarming. It might sound like the end of truth, the collapse of rational discourse, the triumph of postmodern confusion over Enlightenment clarity. But I do not think that is the right way to understand it. The scientists who performed the Prietti experiment were rigorous. They followed strict protocols. They subjected their work to peer review. They published their methods and their data so that others could check their results. All of that still matters. All of that still works. The experiment does not undercut the scientific method. It reveals something about what the scientific method has been doing all along. Science, at its best, is not about discovering capital T truth, in some absolute sense. Science is about building reliable knowledge, about constructing models that make accurate predictions, about testing those models against observation and revising them when they fail. The Prietti experiment does not threaten any of this. It simply clarifies that the knowledge we build might be more contextual, more perspectival, more embedded in the web of observations and observers than we previously realized. And perhaps that is okay. Perhaps that is even liberating. Perhaps the burden of finding the one true description of reality was always too heavy to carry, and letting it go allows us to focus on what actually matters, building knowledge that works, knowledge that helps us navigate the world, knowledge that allows us to flourish together even in a universe whose foundations are stranger than we ever imagined. But let us not move too quickly to comfort. Let us not pretend that the Prietti experiment is easily absorbed, easily integrated, easily reconciled with our everyday experience. The experiment is strange, the implications are uncomfortable, and the conversation about what it means is far from over. In fact, the conversation has intensified since 2019. New experiments have been proposed and some have been performed. Variations on the Wigner's friend scenario have been explored, pushing the boundaries of what can be tested, looking for cracks in the quantum edifice, trying to find the point where reality reasserts itself and objectivity is restored. One direction of research involves making the friend more complex. In the original Prietti experiment, the friend was not a conscious human being, but a collection of optical components that recorded a result and then had that record interfered with. Some researchers have asked what happens if the friend is a genuine artificial intelligence, a system complex enough to have something like beliefs, something like memories, something like perspective. Would the experiment still work? Would the Bell-Wigner inequality still be violated? And what would that tell us about the relationship between consciousness and quantum mechanics? These are difficult experiments to perform, technically and conceptually. We do not yet have artificial intelligences sophisticated enough to serve as true Wigner's friends, but the questions are being asked, the designs are being sketched, and in the coming decades we may see versions of the experiment that push even further into the territory of the strange. Another direction of research involves looking for loopholes that were not previously considered. Perhaps there is something about the way the experiment is set up that allows for a classical explanation after all. Perhaps the violation of the inequality depends on subtle assumptions that, if examined carefully, turn out to be violated. This is always a possibility in experimental science. No experiment is perfect. No measurement is absolute. And skepticism, relentless skepticism, is the engine that drives progress. But so far the skeptics have not succeeded. Every loophole that has been proposed has been addressed. Every alternative explanation has been tested and found wanting. The result stands. And so we arrive at the heart of the matter. The result stands. 5 years after the experiment was published, after conferences argued and theorists debated and skeptics scrutinized every detail, the core finding remains intact. Two observers can record genuinely incompatible facts about the same quantum event, and both records are correct according to the rules of quantum mechanics. This is not a provisional finding waiting to be overturned. This is not a puzzle that cleverer physicists will solve tomorrow. This is what the theory predicts and what the experiment confirms. The question is no longer whether observer-dependent reality is real. The question is what we are going to do about it. Let me take you into one of those conferences where the arguing happened. Picture a room in a hotel somewhere neutral, perhaps Vienna, perhaps Singapore, perhaps one of those anonymous conference centres that physicists seem to migrate to like birds following invisible lines of magnetic force. The room is windowless. The carpet is that particular shade of burgundy that absorbs all hope. There are perhaps 100 people seated in rows of uncomfortable chairs, facing a screen where a speaker is presenting slides covered in dense mathematics. The air smells of coffee that has been sitting too long, and the faint anxiety of people who have spent their careers believing one thing and are now being asked to believe something else. The speaker finishes. The moderator asks for questions, and then it begins. A hand shoots up in the third row. An older physicist, someone who made their name decades ago working on foundational questions, someone whose textbooks are used in graduate courses around the world. They stand up, and their voice carries the weight of authority earned over 40 years of careful work. I don't see how this changes anything, they say. We have always known that quantum mechanics is strange. We have always known that measurement is subtle. What the Prietti experiment shows is simply that we need to be more careful about how we define systems and observers. It does not show that reality is observer-dependent in any metaphysically interesting sense. The speaker at the podium nods politely. They have heard this objection before. They have a response prepared. But before they can deliver it, another hand goes up, this time in the back row. A younger physicist, someone whose career has been built on exactly these questions, someone who has published papers arguing that the implications of the experiment are even stranger than the experimenters themselves acknowledged. With respect, the younger physicist says, and the phrase hangs in the air with that particular tone that means respect is not entirely what is being offered. The Copenhagen interpretation does not actually handle this case. Bohr never addressed scenarios where observers observe observers. The collapse postulate gives you different answers depending on where you draw the line, and the experiment shows that both answers are correct. That is not a matter of being more careful. That is a matter of facing the fact that the framework is incomplete. Now a third hand, somewhere in the middle of the room. This physicist has spent their career on many worlds interpretations, on the idea that every quantum event causes the universe to branch into multiple copies of itself, each copy containing a different outcome. The solution is obvious, they say. Both observers are right because both observers exist. Alice exists in one branch of the universal wave function, recording her result. Bob exists in another branch, or perhaps the same branch, but with a different indexical relationship to the superposition. There is no contradiction because there is no collapse. The wave function never reduces, it simply keeps branching, and each branch contains a consistent history. But that is not what the experiment shows, someone else interjects, not even waiting to be called on. The moderator has lost control of the room. The experiment shows a violation of a Bell-type inequality. That is not about branching. That is about correlations. The correlations are stronger than any local hidden variable theory can explain, which means something non-local is happening, something that connects the two wings of the experiment in ways that cannot be explained by pre-established agreements or by simple branching. Non-locality is not the same as observer dependence. I didn't say it was, I said, the point is that cubism handles this perfectly naturally. Cubism is not a physics interpretation, it is a philosophy of science paper wearing a lab coat. And now, the moderator is standing, trying to restore order, suggesting that perhaps these discussions would be better continued over coffee, that the next speaker is waiting, that there are other presentations to get through, but no one is listening. The room has fractured into half a dozen simultaneous arguments, each cluster of physicists convinced that they have the answer, that the other clusters are missing something obvious, that if everyone would just think clearly for a moment, the whole thing would resolve itself. This is what the Prietti experiment did to physics. Not the quiet, collegial disagreement that characterizes most scientific debates. Something rawer than that. Something that touched nerves that physicists did not know they had, that activated philosophical commitments that most of them had never been forced to articulate, that made the foundations of their discipline suddenly feel less solid than they had assumed. I want you to understand the stakes here. The people in that conference room are not cranks or mystics or people who have lost their grip on rigour. They are among the most careful thinkers on the planet. They have spent their lives developing mathematical frameworks of extraordinary precision and beauty. They have solved problems that seemed impossible. They have built technologies that have transformed the world. And yet here they are, arguing about what it means for something to be true, arguing about whether observers create their observations or merely record them, arguing about whether the universe has a single story, or many stories, or no story at all. The Prietti experiment did not create these disagreements. The disagreements have existed since the 1920s, since the first generation of quantum physicists argued about what their own equations meant. But the experiment sharpened the disagreements. It gave them experimental teeth. It took debates that had been purely theoretical and showed that they could be tested, that nature would weigh in, that philosophy could no longer hide behind the claim that these questions were beyond experimental reach. Let me give you a sense of how the different camps responded to the result. The Copenhagen school, the oldest, and in some ways the most influential interpretation of quantum mechanics, had the hardest time. Niels Bohr, the architect of Copenhagen, had always insisted that quantum mechanics describes our knowledge of reality rather than reality itself. The theory tells us what we can expect to observe, not what exists when no one is looking. This sounds like it might accommodate observer-dependent facts quite naturally. But there is a complication. Bohr also believed in a classical world, a domain of ordinary experience where measurement results are definite and observers agree. The quantum world and the classical world were distinct realms in Bohr's thinking, and the boundary between them, however fuzzy, guaranteed that at the end of the day someone could write down what happened and everyone would agree. The Prietti experiment erases that guarantee. It shows that even in the classical domain, even when results have been recorded and stored, there is no single fact about what happened that all observers must accept. The boundary between quantum and classical does not protect objectivity. It was never doing the work that Copenhagen assumed it was doing. Some Copenhagen adherents responded by retreating further into epistemic interpretations. Quantum mechanics, they said, was never about reality in the first place. It is about information, about updating beliefs, about the relationship between agents and their environments. The Prietti experiment simply confirms what they always suspected, that asking what really happened is a category error, a remnant of classical thinking that quantum physics invites us to abandon. This response has a certain elegance, but it comes at a cost. If quantum mechanics is only about beliefs and predictions, if it tells us nothing about the world independent of observers, then what exactly are physicists doing? What are the equations describing? What makes one theory better than another if not its correspondence to some underlying reality? These are not questions with easy answers, and the Copenhagen school has spent the years since 2019 trying to find a stable position that accommodates the experiment without collapsing into pure instrumentalism. The many worlds interpretation, by contrast, seem to emerge from the experiment in a stronger position. On this view, there is no collapse, no moment when possibilities reduce to a single actuality. The wave function simply evolves according to Schrödinger's equation, branching whenever a measurement occurs, producing a vast tree of parallel histories where every outcome is realized somewhere. In this framework, it is natural that different observers record different results. They exist in different branches. Their facts do not conflict because they do not occupy the same reality. But many worlds has its own difficulties. The interpretation struggles to explain why we should care about probabilities if every outcome happens somewhere. It struggles to explain what it means for a branch to be real if we can never access the other branches, and it struggles to account for the specific structure of the Prietti experiment, where the correlations between Alice and Bob's measurements violate inequalities that seem to require something more than simple branching to explain. Then there is cubism, a more recent interpretation that takes the agent-centered perspective as foundational. On this view, quantum mechanics is a tool that individual agents use to organize their expectations. Probabilities are not objective features of the world, but degrees of belief held by specific reasoners. The wave function is not a physical entity, but a summary of an agent's information and uncertainty. In cubism, there is no mystery about different observers having different facts. Of course they do. Facts are always relative to agents. The universe is not a single story told from a God's eye view. It is a network of interacting perspectives, each with its own web of beliefs and expectations. Cubism handles the Preti experiment with remarkable grace, but critics argue that it achieves this grace by giving up too much. If quantum mechanics only describes subjective beliefs, what ensures that different agents can communicate, that science is possible, that the physical world has any structure independent of the minds that contemplate it? These are deep questions, and the cubists have sophisticated answers, but the debate continues and no consensus is in sight. And then there are the interpretations that take the experiment as evidence for something more radical still. Perhaps the problem is not with our interpretation of quantum mechanics, but with our conception of space and time, with our assumption that events can be located in a single frame, with our belief that the universe has a unique history. Some physicists have responded to the Preti experiment by proposing that reality is fundamentally relational, that properties do not exist until they are observed, and that different observers genuinely create different facts by the act of observation itself. This is the relational interpretation, developed most fully by the Italian physicist Carlo Rovelli. On this view, there is no God's eye perspective from which the universe can be described. Every description is relative to an observer. Every property is a relation between systems. Alice observes the photon and creates one set of facts. Bob observes Alice and creates another set. The facts are not inconsistent because they were never meant to be compared from some external standpoint. The external standpoint does not exist. Stop and feel the weight of that. The external standpoint does not exist. There is no place you could stand, no perspective you could adopt that would give you access to the true facts about what happened. The facts are multiple. They are relational. They are as real as anything gets, but they are not unique. This is the position that the Preti experiment most naturally supports, according to some physicists. The experiment was specifically designed to test a scenario that the relational interpretation handles with ease, and the violation of the Bell-Wigner inequality is exactly what the relational interpretation predicts. If you take the relational view seriously, the experiment is not surprising at all. It is simply confirmation of what the theory always said, but not everyone accepts the relational interpretation. Many physicists find it too permissive, too willing to abandon the goal of a single coherent description of the universe. They argue that science requires objectivity, that without a shared reality we cannot communicate, cannot cooperate, cannot build knowledge that transcends individual perspectives. The relational interpretation, they say, threatens the very foundations of the scientific enterprise. The debate goes on. It will go on for years, perhaps for decades. The Preti experiment did not end the conversation. It intensified it. It raised the stakes. It made clear that the questions about quantum mechanics and reality that physicists had been avoiding for a century could no longer be avoided. Let me take you back to the laboratory for a moment. Picture the optical table after the experiment is done, after the final data has been collected and analysed, after the paper has been written and the press coverage has come and gone. The table is quiet now. The lasers are off. The crystals sit in their mounts, inert, waiting for the next experiment. The photons that violated the inequality have been absorbed by detectors and dissipated into the thermal background of the room. Their journey is over. But the question they raised remains. What happened to those photons? Did they have a definite polarization before they were measured, or did the measurement create the polarization? Did the friend in the middle of the experiment know something real? Or was her knowledge an illusion that dissolved when Wigner interfered with her record? Was there ever a single story about the experiment? Or were there always multiple stories, branching and weaving and never quite converging into a single thread? The experiment cannot tell us which interpretation is correct. It can only tell us which interpretations are ruled out. And what it rules out is the comfortable assumption that there is always a fact of the matter, that observers are passive witnesses to an independent reality, that disagreements can always be resolved by looking more carefully at the evidence. Some of that comfort is gone now, some of that certainty has been surrendered, and the physicists who work on these questions have had to learn to live with a universe that is stranger, more elusive, more resistant to final description than the universe they were trained to expect. I want to tell you about one more conversation, one that happened not at a conference but in a quiet room, late at night, between two physicists who had spent their careers on opposite sides of this debate. I am imagining this conversation, constructing it from interviews and papers, and the general shape of how these arguments unfold. But the substance is real, even if the specific words are invented. One physicist believes in an objective reality. They believe that quantum mechanics is incomplete, that there must be hidden variables or deeper laws or some modification of the theory that restores the picture of a single, observer-independent world. They have spent their life looking for that modification, and they have not found it, but they believe it must exist because the alternative is unthinkable. The other physicist has made peace with observer dependence. They believe that the Proietti experiment confirms what quantum mechanics has been telling us all along, that reality is relational, that facts are perspectival, that the dream of a God's eye view was always an illusion we inherited from classical physics and never should have taken for granted. They are sitting across from each other, glasses of wine on the table, the equations exhausted, the arguments familiar, the disagreement as sharp as ever. "Tell me this," the first physicist says. "If there is no single fact about what happened in the experiment, if Alice and Bob can both be right even though they disagree, then what is physics describing? What is the theory about?" "The theory is about relationships," the second physicist replies. "It tells us what any observer can expect to experience given what they have previously experienced. It does not need to tell us what the universe is like when no one is looking, because that question does not have an answer. Or rather, it has many answers, one for each possible observer, and they are all equally valid. But we can talk to each other," the first physicist objects. "We can compare notes. We can build on each other's work. How is that possible if we do not share a reality?" "We share enough," the second physicist says. "Our realities overlap sufficiently that communication is possible, that science is possible, that we can sit here and have this conversation. The overlap is not total. There are gaps, contradictions, places where my facts and your facts do not quite mesh. But that has always been true. We just did not have an experiment that made it undeniable." The first physicist is silent for a moment, turning their glass in their hand, watching the light refract through the wine. When they speak again, their voice is quieter. "It is a loss," they say. "Even if you are right, even if the relational interpretation captures the truth about quantum mechanics, it is a loss. We grew up believing in a universe we could understand, a universe with a single story, a universe that would yield its secrets to patient inquiry. And now you are telling me that the universe does not have a single story, that it has as many stories as there are observers, that the secrets I thought I was uncovering were always partly my own reflection." "Perhaps," the second physicist says, "or perhaps it is not a loss. Perhaps it is a discovery. Perhaps we have found something true about the universe, something we could not have found without the experiment, something that changes what it means to do physics and what it means to be a physicist. That is not nothing. That is a gift, even if it comes wrapped in discomfort." The conversation does not end with agreement. It rarely does. The two physicists finish their wine, shake hands, return to their separate hotels and their separate careers. The next morning they will present at the same conference, argue about the same equations, disagree about the same fundamental questions. But something has shifted, perhaps. Some small understanding has grown in the space between them. The universe is strange. The experiment has confirmed it, and the work of understanding continues. But here is the thing about the work of understanding. It does not move in straight lines. It does not proceed from confusion to clarity in the way textbooks suggest. Sometimes the work of understanding is the work of sitting with a result that refuses to make sense, turning it over and over in your hands, looking for an angle from which it becomes less strange. And sometimes you never find that angle. Sometimes the strangeness is the answer. The Proietti experiment was published in February 2019. By March, the responses had begun. They came as preprints, as conference talks, as arguments over coffee, as late-night emails between collaborators who could not quite believe what they were reading. And the responses fell into patterns that were, in retrospect, entirely predictable. Because the scientific community had been preparing for this moment for decades, had been mapping out the logical space of possible reactions, had been sharpening the arguments for and against each interpretation, until they gleamed like well-honed knives. Some physicists dismissed the result entirely. Not the data. The data was solid, reproduced, checked, and rechecked until there was no room for error. What they dismissed was the interpretation. The claim that the experiment showed incompatible realities, they argued, was an overreach. The experiment showed correlation, certainly. It showed a bell-like violation, certainly. But the leap from those correlations to the claim that two observers recorded genuinely different facts about the same event, that leap, they insisted, was philosophical, not physical. You could tell a story about the experiment in which there was always a single reality, even if that reality was complicated, even if it involved entanglement and interference and all the other strangeness of quantum mechanics. The strangeness of quantum mechanics, after all, was old news. The double-slit experiment was strange. Schrödinger's cat was strange. Bell's theorem was strange. Why should this experiment be any different? The answer, when it came, was quiet but devastating. This experiment was different because it targeted assumptions that the other experiments had left untouched. The double-slit experiment showed that particles could behave like waves. Schrödinger's cat showed that superposition could apply to macroscopic systems, at least in principle. Bell's theorem showed that reality was non-local in some deep sense, that quantum correlations could not be explained by local hidden variables. But none of those experiments directly addressed the question of whether different observers could disagree about the outcome of a measurement. None of them constructed a situation in which Alice's record and Bob's record were both definite, both obtained through valid measurements, and yet contradicted each other in a way that violated a mathematical constraint derived from the assumption of consistency. The Proietti experiment did exactly that. It took the Bruckner-Frauchiger chain of logic, the assumption that measurements have single outcomes, the assumption that those outcomes can be used by other observers, the assumption that quantum mechanics applies universally, and it tested whether those assumptions held together under pressure. And the answer was no. Not in a subtle, statistical, barely visible way. The violation was 5 standard deviations. The violation was overwhelming. The violation screamed at you from the data. So the dismissals did not stick. They were made, and they were answered. And slowly the scientific community had to confront the fact that something real had been demonstrated in that laboratory in Edinburgh. Something that demanded an explanation. And the explanations came. They came in floods. From the Everettians, the many worlds advocates, the explanation was almost triumphant. Of course, Alice and Bob recorded different outcomes. Of course, their realities diverged. That is what happens when a quantum measurement occurs. The universe branches, and each branch contains its own version of the observer with its own definite record. Alice's record is definite in her branch. Bob's record is definite in his branch. There is no contradiction because there is no single Alice and no single Bob. There are many Alice, many Bobs, each living in their own branch of the universal wave function, each unaware of the others except through the strange correlations that experiments like Proietti's can reveal. The many worlds interpretation had always claimed this. It had always insisted that superposition never collapses, that the appearance of collapse is an illusion generated by decoherence and branching, that the universe is far vaster and stranger than it appears from within any single branch. The Proietti experiment from this perspective was simply a confirmation of what the interpretation had always said. The uncomfortable implications, the exponential proliferation of branches, the infinite copies of every person who has ever existed, the impossibility of assigning a single history to the universe, those implications had always been there. The experiment did not create them, it simply made them harder to ignore. But the many worlds interpretation has its own discomforts, and its critics were quick to point them out. If every measurement causes the universe to branch, then how do we make sense of probability? In a deterministic branching process, every outcome happens with certainty in some branch. What does it mean to say that one outcome is more likely than another if both outcomes are guaranteed to occur? The Everettians have answers to this question, elaborate mathematical frameworks involving decision theory and branch counting and self-locating uncertainty. But the answers are controversial, and not everyone finds them satisfying. The Proietti experiment did not resolve this debate. It simply raised the stakes. From the Bohmians, the pilot wave theorists, the response was more cautious. The Bohmian interpretation holds that particles have definite positions at all times, guided by a wave function that evolves according to the Schrödinger equation. In this picture, there is always a single reality, the positions of all the particles in the universe, even though that reality is hidden from us, only partially accessible through measurements that disturb the system. The Bohmian response to the Proietti experiment was to insist that somewhere in the analysis, an assumption was being made that the Bohmian picture did not actually require. Perhaps the measurement records were not as straightforward as they appeared. Perhaps the interference measurements that reversed Alice's observation were doing something more subtle than simply restoring a superposition. Perhaps, in the Bohmian picture, there was a consistent story to be told about what actually happened, even if that story was complicated and counterintuitive. The trouble was, such a story proved difficult to construct. The Bohmian mechanics is non-local. It has to be to evade Bell's theorem. But the non-locality in the Prietti setup seemed to require something more. It seemed to require that Alice's measurement outcome, once recorded, could be unrecorded, that the particle position that had been revealed could become concealed again, that the definite reality the Bohmians prize could fluctuate in ways that their framework was never designed to accommodate. Some Bohmian physicists took this as a challenge, an opportunity to extend the formalism in new directions. Others quietly began to wonder whether the interpretation could survive in its original form. From the Cubists, the quantum Bayesians, the response was almost serene. Cubism had always insisted that quantum states are not descriptions of reality, but descriptions of an agent's beliefs about what they will experience. The wave function is not a physical object. Probabilities are not frequencies. Measurements are not passive observations, but active interventions that reshape the agent's relationship with the world. From this perspective, the Prietti experiment showed exactly what you would expect. Alice has her experiences. Bob has his experiences. Their experiences are different because they are different agents with different perspectives. There is no mystery here, no paradox, no crisis. Only the familiar Cubist insight that physics is first personal, that the view from nowhere was always a fantasy. But the Cubist response invited its own questions. If Alice's record and Bob's record are both valid, both representing genuine experiences, then what is the relationship between them? Are they experiencing the same world? Different worlds? Is there any sense in which one of them is wrong? The Cubists say no. They say that the question presupposes a God's-eye view that does not exist, that asking what really happened is asking for something physics cannot provide. But this answer, however internally consistent, strikes many physicists as a retreat. It seems to give up on the project of describing a world that exists independently of our observations, a world that science has always assumed was there, waiting to be understood. And then there are the interpretations that take the experiment as a sign that something must be changed. Not just reinterpreted, but changed at the level of the fundamental equations. Objective collapse theories, theories that posit a physical mechanism for wave function collapse, something that happens spontaneously, something that prevents superpositions from building up to macroscopic scales. These theories have always been the underdogs of quantum foundations. They lack the elegance of many worlds, the determinism of Bohmian mechanics, the philosophical radicalism of cubism. But they have one virtue that the Prietti experiment suddenly made more attractive. They promise a single reality. If wave functions collapse objectively, then Alice's measurement truly does create a definite outcome, an outcome that Bob cannot undo, an outcome that is part of the single shared reality we all inhabit. The Prietti experiment from this perspective was a challenge. If objective collapse is real, then the experiment should not have shown the correlations it did. The interference patterns that Bob observed should have been destroyed by Alice's measurement, by the collapse that occurred when she looked inside the box. The fact that the correlation survived, that the Bell-like inequality was violated, suggested that collapse did not happen when and where these theories predicted it would. But wait, said the collapse theorists. The collapse in their models depends on the mass of the system, on the number of particles involved, on parameters that can be adjusted. Perhaps the photon-based system in the Prietti experiment was simply too small, too delicate, too protected from the collapse mechanism for the predicted effects to appear. Perhaps a more massive system, a system involving actual conscious observers, rather than photonic proxies, would show different results. Perhaps the next experiment, the one with heavier particles, with longer decoherence times, with true macroscopic measurements, would vindicate the collapse picture after all. This was the state of affairs in the months and years following the publication. Not resolution, but proliferation. Not consensus, but fragmentation. Every interpretation found a way to accommodate the result, and every accommodation came at a cost. The many worlds advocates paid in branches, accepting an infinite proliferation of realities. The Bohmians paid in non-locality, accepting that their hidden variables must behave in ways that strain intuition. The cubists paid in realism, accepting that physics cannot tell us what the world is like, only what we should expect to experience. The collapse theorists paid in uncertainty, hoping that future experiments with larger systems would rescue their picture of a single world. And the Copenhaganists, the physicists who simply use quantum mechanics without committing to any interpretation, who insist that the formalism is complete and the metaphysical questions are meaningless, they paid in silence. They had no response, really. They had only the observation that the experiment worked, that the predictions held, that physics continued to function even without answers to the deep questions. They shrugged, and they turned back to their calculations, and they left the philosophers and the foundationalists to argue about what it all meant. But the argument did not stay contained. It spilled out of the seminar rooms and the conference halls. It seeped into the broader culture, into popular science articles and YouTube videos and late-night conversations between people who had never heard of Bell's theorem but had heard, somehow, that reality was not what it seemed. The phrase that circulated was variations on a theme. Quantum mechanics says reality isn't real. Science proves that truth is subjective. Two people can disagree about what happened and both be right. These phrasings were imprecise, of course. They mangled the subtleties, collapsed the distinctions, made the result seem more mystical than it was. But they captured something, too. They captured the genuine discomfort that the experiment had produced. They captured the sense that something fundamental had shifted, that the ground we had always assumed was solid had turned out to be less stable than we thought. Because here is what the Proeti experiment actually showed, stripped of interpretation, stated as plainly as possible. If you assume that measurements have single outcomes, and if you assume that those outcomes can be combined across observers using classical logic, and if you assume that quantum mechanics is universally valid, then you can derive a mathematical constraint that the experiment violates. The violation means that at least one of those assumptions is wrong. But the experiment does not tell you which one. It simply demonstrates that the package deal, single outcomes, classical logic, universal quantum mechanics, is internally inconsistent. And that is the source of the disagreement, the cause of the argument that has continued for years. Each interpretation chooses a different assumption to abandon, a different piece of the package to sacrifice. The many-worlders abandon single outcomes. The cubists abandon the idea that Alice's and Bob's perspectives can be combined into a God's-eye view. The collapse theorists abandon universal quantum mechanics, hoping to find a scale at which the theory breaks down. The Bohmians abandon something harder to name. Perhaps the idea that measurements reveal pre-existing facts rather than creating facts anew. And the physicists at the conference, the ones who argued late into the night, the ones who sat across from each other with their wine and their exhaustion, they were not just arguing about interpretations. They were arguing about what physics is for. Is physics a tool for making predictions? A machine that takes initial conditions as input and spits out expected observations as output? If so, then the interpretive questions are secondary, perhaps even meaningless. The machine works. That is what matters. Or is physics an attempt to understand the world, to tell a story about what exists and how it behaves, to provide a picture of reality that makes sense to creatures like us who evolved to navigate a world of medium-sized objects at medium speeds over medium distances? If so, then the interpretive questions are essential, are the whole point of the enterprise. And the Proeti experiment has just demonstrated that we cannot tell that story, at least not in the way we thought we could. This is the divide that runs through the heart of physics, invisible most of the time, papered over by the everyday success of the formalism. But events like the Proeti experiment make the divide visible. They force physicists to choose sides, or to articulate why they refuse to choose, or to change their minds, or to dig in deeper. They force conversations that would otherwise be avoided, questions that would otherwise be dismissed as philosophical rather than physical. There is a word for what the Proeti experiment did to the foundations of physics. The word is clarify. The experiment did not resolve the mystery. It clarified the stakes. It demonstrated that the mystery is not a quirk of interpretation, not a matter of taste, not a debate that can be safely ignored. It is a feature of the formalism itself, a consequence of the mathematics when pushed to its logical conclusion. The disagreement is not going away. It cannot be resolved by better technology or smarter theorists or more precise measurements. It is built into the structure of the theory, waiting for us every time we ask what happened. what really happened when Alice looked inside the box and Bob measured the whole system, and their answers refused to match. And perhaps, in the end, that is the gift. Not an answer, but a question. Not a resolution, but a sharpening. Not the comfortable illusion that physics will one day tell us exactly what the world is like, but the uncomfortable truth that physics may have discovered something stranger, that the world is not the kind of thing that has a single description, that facts are more fragile than we thought, that the universe permits divergent experiences without providing a way to reconcile them. The two physicists, the ones who argued late into the night, the ones who disagreed about everything that mattered, they both know this. They have lived with this knowledge for years. They have incorporated it into their work, their teaching, their sense of what it means to be a scientist. And when they shake hands and return to their separate hotels and their separate careers, they carry the same experiment with them, the same data, the same violation, the same 5 standard deviations that demonstrate something neither of them can fully explain. The work continues. It has to. That is what physics does. It takes the confusion and turns it into questions, takes the questions and turns them into experiments, takes the experiments and turns them into more confusion, deeper confusion, better confusion. And somewhere in that cycle, perhaps, understanding grows. Not the kind of understanding that answers every question, not the kind that provides a single story, not the kind that satisfies the hunger for certainty that drives us into science in the first place, but something. A kind of wisdom, maybe. A recognition that the universe is stranger than we expected, that our intuitions are not always guides, that the project of physics may never be complete in the way we once hoped. The Edinburgh laboratory is quiet now. The photons have been switched off. The apparatus sits waiting for the next experiment, the next test, the next attempt to push the boundaries of what we know. Outside the windows, the city goes about its business, unaware that something remarkable happened here, something that will be argued about for decades, something that changed what it means to do science in the 21st century. And somewhere, in a conference room or a coffee shop or a quiet office, lit by the glow of a computer screen, a physicist is staring at the data, trying to make sense of what it means. They have their favourite interpretation. They have their arguments. They have their reasons for believing what they believe. But underneath all of that, in the quiet place where certainty gives way to wonder, they know that the experiment has shown them something they cannot quite name. Something about reality. Something about knowledge. Something about the strange, beautiful, impossible universe we find ourselves trying to understand. The conversation continues, the disagreement persists, and the question hangs in the air, unanswered, perhaps unanswerable. What actually happened when Alice opened the box? The question hangs there, suspended in the silence between breaths, and we could leave it there, could let it float forever in that uncomfortable space where philosophy meets physics, and neither one blinks. But there is more to say. There is always more to say when you are standing at the edge of what humans can know, staring down into the darkness where certainty dissolves. Because the Prietti experiment did not simply produce a result and then fade into the background hum of academic physics. It produced a result that landed like a stone thrown into still water, and the ripples are still spreading, still disturbing the surface, still reaching shores that the experimenters themselves never anticipated. In the months after the paper appeared, something unusual happened. The kind of thing that does not happen often in modern physics, where specialization has carved the discipline into 1,000 narrow corridors, and most scientists spend their careers exploring a single hallway, never venturing into the rooms on either side. What happened was this. People started talking. Not just quantum physicists, not just the specialists who had spent decades arguing about measurement and collapse and the role of the observer. Philosophers, mathematicians, computer scientists, people who had always suspected that the foundations of physics contained something unresolved, something that the textbooks papered over with reassuring language about experimental irrelevance and interpretive freedom. They looked at the Prietti data and they saw what Wigner had seen 6 decades earlier, what Bruckner had formalised, what the Edinburgh laboratory had finally demonstrated. They saw that the comfortable assumption underlying all of modern science, the assumption that experiments have outcomes, that those outcomes are facts, that facts are the same for everyone, was not a discovery, but a hope that the universe had never promised to fulfill. The conferences that followed were unlike anything the field had seen in years. Not the polite exchanges of technical refinements that characterize most academic meetings, where researchers present incremental advances and the audience nods and asks gentle questions and everyone goes home feeling that progress has been made. These conferences were different. These conferences featured arguments. Real arguments, the kind where voices rise and faces flush, and senior physicists interrupt junior ones and nobody leaves the session, feeling that anything has been settled. Because nothing had been settled. The experiment had settled nothing except the question of whether the Wigner's friend scenario could be realized in a laboratory. And the answer to that question, yes, it can. Yes, we did it. Yes, the data is here. Opened up every other question like a wound that had never properly healed. Picture one of these conferences. Not in your imagination, but in the world. Because it happened. Because it is still happening. Because the arguments that began in 2019 are still echoing through lecture halls and seminar rooms, and the late-night conversations of physicists who cannot sleep, because the universe refuses to make sense. Picture a room full of people who have devoted their lives to understanding reality, who have spent decades learning the mathematics, who can manipulate the formalism with the fluency of native speakers. Picture them looking at the same data, the same violation, the same 5 standard deviations, and arriving at conclusions so different that you would think they were looking at different experiments entirely. One group says, the experiment proves that quantum mechanics is incomplete, that there must be additional variables, hidden structures, something the theory does not describe but that determines in principle what actually happens when a measurement occurs. These people point to the violation of the Bell-Wigner inequality as evidence that the standard assumptions, the assumptions of locality, of observer independence, of a single consistent reality, cannot all be true. At least one must go, and they have their preferences. They have their reasons for preferring one sacrifice over another, reasons rooted in decades of theoretical work and philosophical intuition, and the deep conviction that the universe, whatever it is, must be coherent at some fundamental level. Another group says, the experiment proves nothing of the sort, proves only that the extended Wigner's friend scenario produces the results that quantum mechanics predicts, which we always knew it would, which is why we conducted the experiment in the first place. These people argue that the violation is not evidence of anything wrong with quantum mechanics, but evidence of something wrong with our classical assumptions, our naive belief that measurements produce unique outcomes that exist independently of who is asking. The theory works, the predictions are confirmed, what more do you want? And then there is a third group, smaller perhaps but no less certain, who say, the experiment proves that quantum mechanics, as currently formulated, is not a complete description of nature, but a tool for making predictions, a calculus of expectations, an instruction manual for what to expect when you perform certain operations. On this view, the theory was never meant to tell you what actually happens. It was only ever meant to tell you what you will observe when you look, and the question of what happens before you look, between looks, when someone else looks, is not a question the theory answers because it is not a question physics can answer. Not yet. Maybe not ever. 3 groups, 3 interpretations, 3 ways of understanding the same data, the same experiment, the same violation of the same inequality. And here is the remarkable thing, the thing that would have astonished physicists a century ago, the thing that still astonishes anyone who thinks carefully about what science is supposed to do. The experiment does not adjudicate between them. The experiment cannot tell you which group is right. The experiment cannot tell you whether reality is non-local, or observer-dependent or fundamentally uncertain. It can only tell you that some combination of classical assumptions is false, and it leaves all of us, in the uncomfortable position of choosing which assumptions to sacrifice. This is not how physics is supposed to work. At least this is not how physics is supposed to work in the stories we tell about it. The triumphant narratives of progress and discovery. The textbook histories that move from confusion to clarity like a train on a track. In those stories, experiments resolve disputes. Data settles questions. The universe speaks and the physicists listen, and eventually, sometimes after years or decades of argument, a consensus forms, and the dispute is over, and the textbooks are updated, and science moves on. But the Prietti experiment has not resolved a dispute. It has formalized one. It has taken a question that physicists could once pretend was merely philosophical, and demonstrated that it is also empirical, that it produces measurable results, that those results violate inequalities, and that the violation leaves us exactly where we started, in the presence of a mystery we cannot explain. Stop and feel the weight of that. This is not a failure of the experiment. This is what the experiment discovered. The universe permits divergent descriptions. The formalism predicts disagreement. The data confirms the prediction. And the meaning of the data, what it tells us about reality, about knowledge, about the strange boundary between the world and our experience of it, remains as contested now as it was the day Wigner first posed his question in that quiet Princeton office in 1961. There is something almost vertiginous about this situation, something that can make you dizzy if you think about it too carefully. We're accustomed to believing that physics, whatever its other limitations, whatever its mathematical abstractions and its unfamiliar language and its experiments conducted in laboratories most people will never see, that physics, at its core, describes an objective reality, a reality that exists whether we observe it or not, a reality that has definite properties, definite states, a definite history that unfolds according to laws we can discover. This belief is so deep, so foundational, that most of us never question it. It is the ground on which modern science stands, the assumption that makes the entire enterprise feel worthwhile. We do physics because we want to know what the universe is like. We want to know the truth, but what the Prietti experiment suggests, what it demonstrates, in the precise language of inequality violations and statistical significance, is that this belief may be too simple, may be in fact a kind of hope dressed up as an axiom. Because if observer-independent facts do not exist at the quantum level, if Alice's measurement and Bob's measurement can yield genuinely incompatible realities, then the question of what the universe is like does not have a single answer. It has many answers, incompatible answers, answers that depend on where you stand and what you measure and when you ask. And the dream of a complete description, a God's eye view, a theory of everything that would finally tell us what is really going on, that dream may be not just unfulfilled but unfulfillable. Let that settle for a moment, because this is the moment where the story we have been telling, the story of two physicists and a thought experiment in a laboratory in Edinburgh, connects to something larger, something about what science is, something about what knowledge means, something about the strange position we find ourselves in 2 decades into the 21st century, when our most successful theory of nature, the theory that describes everything from the colour of stars to the chemistry of life, to the computer you're watching this on, when that theory refuses to tell us what actually exists. The working physicist, the one running experiments and writing papers and teaching students, has a way of coping with this situation. They focus on predictions, they focus on calculations, they focus on the parts of the theory that work brilliantly, that produce results with staggering accuracy, that have never once failed when tested against observation. And they set aside the interpretive questions, the philosophical puzzles, the Ignor's friend scenarios that seem so distant from the practical work of doing physics. This is not cowardice or evasion. It is pragmatism. It is the recognition that you can use a tool without fully understanding how it works, that you can drive a car without knowing the details of the internal combustion engine, that the success of quantum mechanics does not depend on resolving its foundational mysteries. But the Prietti experiment makes this strategy harder, not impossible. Physicists are nothing if not skilled at compartmentalization, but harder. Because the experiment takes the abstract puzzles and makes them concrete. It takes the thought experiments and turns them into data. It takes the questions that could once be dismissed as philosophical luxuries and demonstrates that they have measurable consequences, that they affect real numbers in real laboratories, that they produce violations of real inequalities derived from real assumptions about the nature of facts and the consistency of descriptions. The mystery is no longer floating somewhere in the philosophy department, waiting for the physics to be finished before it needs to be addressed. The mystery is here, in the data, in the formalism, in the very predictions that make quantum mechanics so successful. And so, the conversation continues. It has to. Not the polite conversation of incremental progress, but the difficult conversation of fundamental disagreement. The conversation where senior physicists admit that they do not know, where junior physicists are free to propose radical alternatives, where the comfort of consensus gives way to the discomfort of genuine uncertainty. In the years since the experiment, papers have multiplied. Not just reanalyzing the data, not just proposing improved versions of the apparatus, but attempting something more ambitious to find a way out. A new axiom that resolves the tension, a modified theory that predicts something different, a conceptual framework that makes the disagreement disappear. So far, none of these attempts has succeeded. The frameworks that resolve the Wigner's friend paradox tend to create new problems of their own. The modified theories tend to make predictions that conflict with other experiments. The new axioms tend to feel arbitrary, as if we're patching holes in a dam that keeps springing new leaks. The situation is, as the physicists say, unsettled, which is a polite way of saying that nobody knows what to do, but perhaps, and this is the thought that keeps some physicists awake at night, the thought that feels like either wisdom or despair depending on the hour, perhaps the situation is not meant to be settled. Perhaps the Proietti experiment has revealed something true. Not true in the sense of answering a question, but true in the sense of showing us what kind of questions we're asking. We have been assuming for 400 years that the project of physics is to describe the world, to build a picture of reality that is independent of the observer, that would be true whether anyone was looking or not, that represents the universe as it actually is rather than as it appears to any particular perspective. This assumption is the inheritance of Galileo and Newton and Einstein, the belief that nature is written in the language of mathematics and that our job is to learn to read it. But what if that assumption is wrong? What if the universe is not the kind of thing that has a single description? What if the project of physics is not to build a view from nowhere, but to understand the relationships between views, the ways that different perspectives can be compatible or incompatible, the rules that govern what any given observer will experience when they perform any given measurement? This is not mysticism. This is not a rejection of science. It is a revision of what science is for, a recognition that the universe may be stranger than our intuitions, that the hope for a God's eye view may be exactly that, a hope, and that maturity might consist not in achieving that view, but in accepting that it may not exist. The two physicists, our two physicists, the ones who argued late into the night about what the experiment means, they have both considered this possibility. It would be impossible not to. When you spend your career studying the foundations of quantum mechanics, when you grapple daily with the measurement problem and the role of the observer, and the strange way that the formalism seems to require someone to look before outcomes become definite, you cannot avoid the question of whether the universe is fundamentally perspectival, whether facts are always facts for someone, whether the dream of objective reality is a dream we need to wake up from. One of them finds this possibility liberating. Not a defeat, but a discovery. A recognition that the universe is richer than we thought, that it contains room for multiple consistent descriptions, that the absence of a God's eye view is not a failure, but a feature. On this reading, the Proietti experiment is not bad news. It is important news. It is telling us something true about the nature of knowledge, about the relationship between observers and systems, about the limits of what any finite being can know about an infinite cosmos. The other physicist finds the same possibility troubling, not because it is impossible to live with, but because it seems to undermine the very thing that drew them to physics in the first place. The conviction that there is a truth out there, that the universe has a definite character, that our theories are not just tools for prediction but windows onto reality, imperfect windows perhaps, smudged and distorted, but windows nonetheless. To give up on this conviction feels like giving up on physics itself, or at least on the physics they signed up for, the physics of Einstein and Feynman and all the others who believed that nature was comprehensible, that the rational structure of the universe could be grasped by rational minds, that the project would one day be complete. They are both right, in their way. They are both wrong. The universe does not care about their preferences, does not adjust itself to make them comfortable, does not offer guarantees that the questions we most want to answer are questions with answers. It simply is what it is, whatever that means, and the experiment has shown us a piece of that isness, a strange dark corner where the familiar rules break down and the comfortable assumptions fail. The Edinburgh laboratory is empty now, not abandoned but waiting. The apparatus that produced the historic measurement still sits in its place, could be switched on tomorrow, could generate more data, more violations, more evidence for a conclusion that no one can fully accept. Outside the windows, the seasons have changed. The students who helped run the experiment have graduated, moved on, taken positions at other universities, carried the knowledge of what they witnessed to other laboratories and other research programs. The paper has been cited hundreds of times. The inequality violation has been confirmed by other groups in other countries using different techniques. The result is not in doubt. Only the meaning is in doubt. Only everything is in doubt. And somewhere, at this moment, in a quiet room lit by the glow of a computer screen, a young physicist is reading about the experiment for the first time. They do not yet know what to make of it. They have been taught quantum mechanics in the standard way, have learned the formalism, have solved the equations, have accepted the strange predictions without fully grappling with what they imply. And now they are encountering Wigner's friend. Now they are seeing the inequality. Now they are understanding, perhaps for the first time, that the theory they have learned does not simply describe an unfamiliar world, but describes a world that refuses to be pinned down, a world where facts depend on observers and observers disagree and no one can say who is right. They feel something shift inside them, a recalibration, a recognition that the path ahead is stranger than they expected, that the questions are deeper, that the comfortable certainties of the textbooks are not certainties at all, but working assumptions, useful fictions, maps that may or may not correspond to the territory. And they have a choice to make, the same choice that every physicist makes when they encounter the foundations of quantum mechanics. They can look away, focus on calculations, treat the interpretive questions as irrelevant luxuries, build a successful career without ever returning to this moment. Or they can look closer, can follow the thread wherever it leads, can accept that the universe may never give them the answers they want and search for them anyway. Both choices are valid. Both choices have produced great physics, and neither choice will resolve the question that hangs in the air of that quiet room, the same question that hung in the air of Wigner's office in 1961, the same question that the Prietti experiment illuminated without answering. What actually happened when Alice opened the box? The universe does not say, the formalism does not say, the data does not say, and perhaps that silence is itself the answer. Not an answer we wanted, not an answer we expected, but an answer nonetheless. The universe is telling us something, telling us through the violation of an inequality, through the disagreement of observers, through the statistical evidence that facts are not what we thought they were. It is telling us that the question may be malformed, that the assumption behind the question, the assumption that something definite happened, that there is a truth of the matter, that reality has a single story to tell, may be the very assumption that needs to be reconsidered. This is hard. It is meant to be hard. The universe is under no obligation to be intuitive, to conform to the categories we inherited from everyday life, to provide the kind of simple answers that satisfy the part of us that wants to know, that needs to know, that cannot rest until everything is clear. The universe simply presents itself, strange and beautiful and impossible, and waits for us to catch up. The work continues. It has to. That is what physics does, what science does, what the human project of understanding does. It takes the confusion and turns it into questions, takes the questions and turns them into experiments, takes the experiments and turns them into more confusion, deeper confusion, better confusion. And somewhere in that cycle, understanding grows. Not the kind of understanding that answers every question, not the kind that satisfies the hunger for certainty, but a kind of wisdom, a recognition of limits, a willingness to live in the presence of mystery without demanding that the mystery resolve itself on our schedule. The two physicists who argued are older now. Their arguments have softened into something like mutual respect, the respect of two people who have spent years wrestling with the same impossible problem and have come to understand that the other's perspective, however wrong it seems, is not stupid, is not careless, is simply a different way of standing at the edge of the unknown and trying to make sense of what lies beyond. They still disagree. They will always disagree. And in that disagreement is something precious, something that the experiment revealed but did not create. The recognition that physics, at its deepest level, is not a finished story, but an ongoing conversation. Not a set of answers, but a collection of questions, refined and sharpened and tested against the world, never final, never complete, always reaching for something just beyond its grasp. The city of Edinburgh goes about its business. The laboratory waits. The data sits in its databases, ready to be analysed again, ready to yield the same violation, the same 5 standard deviations, the same evidence for a conclusion that changes everything and nothing. And the question remains, not as a failure, not as an embarrassment, but as a gift. The gift of knowing that we do not know. The gift of standing at the edge of understanding and looking out at something vast and strange and irreducible to simple stories. The gift of a universe that is stranger than we expected, richer than we hoped, more mysterious than our best theories can capture. What actually happened when Alice opened the box? You will not find the answer in any textbook. You will not find it in any paper or any lecture or any conversation between physicists who have devoted their lives to the question. You will find only the question itself, refined and sharpened and demonstrated in a laboratory in Edinburgh in the year 2019, when a team of physicists proved that the universe permits divergent realities and offers no way to reconcile them. The silence that follows is not empty. It is the sound of the universe, keeping its secrets.